Hey, Professor Lehman. My name is Nathan Reynolds. I am in your ME360 class, and this is video presentation number 2. I apologize if my voice is kind of hard to understand. Pretty under the weather right now, as you could probably tell. But it's the last project. I didn't really want to ask for an extension, just to get it over with. All right, here we go. So, water is pumped from the large tank shown in diagram A, right there. Entrance to the pipe section is sharp-edged. The pipe is cast iron with a total length of 2.0 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and actual head rise is provided in the pump specifications in diagram B. Determine the volumetric flow rate for the system, part A. Okay. So what I did when I was practicing this was start with Bernoulli equation, but in Bernoulli equation you have to account for the head gain from the pump and the head loss due to major and minor losses, and those end up like equaling out because of conservation of energy. But goes like this: P1 over rho g plus V1 squared over 2g plus Z1 plus head from pump HP equals P2 over rho g plus V2 squared Z2 plus head loss. So in this problem, I'm just going to make point 1 here and point 2 here, the exit. So let's start canceling out some stuff. P1 is equal to P2 because they're both equal to the atmosphere, so this term just goes away. V1 we can just assume is 0 because it's not really moving yet. Just move it up there. That's about it, honestly. We could move Z1 over there. I could Z2 minus C1. Yeah, so it's the equation that we simplified down to. Head gain pump equals V2. And instead of writing V2, I'm just going to write V, so I can just stand in for the average velocity, squared over 2g plus Z2 minus C1 plus head loss. So, I forgot to mention part A is determine the volumetric flow rate of the system. And the easiest way to do that is to solve for V by getting head gain and head loss in terms of V, solving for V, and then multiplying it by the area of the pipe. So let's go ahead and do that. I'm going to write down my givens first, just like values that are going to be important. Length is equal to 2 meters. KL, we're going to need that. That's in the book, I believe. Let me find it. Figure 8.22. Since the entrance flow is sharp-edged, KL equals 0.5. That's going to come into play when we do our minor losses, I believe. also from the book. Oh, we're gonna have to use the Moody diagram eventually, so equivalent roughness for cast iron is 0.26 millimeters. Diameter of the pipe is 0.07 meters. And then the area of the pipe is pi over 4 times diameter squared, which comes out to be 0.00385 meters squared. All right, where do I go from here? So from this graph, the relationship between volumetric flow rate and actual head rise, we see that head rise equals 20 minus 2,000 Q squared. So that's the same as saying 20 minus 2,000 AV squared, in parentheses, AV squared. So that's how I'm going to get this into V. And then HL is the major losses plus the minor losses. And major losses major is the friction factor times the length of the pipe times V squared over diameter of the pipe times 2G, and then H minor. Only minor loss we really need to worry about is the entrance of the pipe. And last minor is KL times V squared over 2G. It's L. Substituting these in, so the only unknown is V. 20. All right, and then I think we have all our values. Let's see, delta Z is 6 because of the change in elevation. Friction factor, we need to do friction factor. All right, so on the Moody diagram, since this is wholly turbulent, it's going to be on the right side. I don't have a picture, otherwise I would show you, but you know what it looks like. The right side is wholly turbulent, so like the graph is flat. So the roughness factor, equivalent roughness over diameter is just gonna go straight across. to find the friction factor. So it doesn't rely on Reynolds number when it's wholly turbulent. So that's why we don't have to find Reynolds number. But let me just do this right here. This equals don't forget that this is millimeters and this meters. Excuse me. Grab water real quick. All right, much better. Not much better, but a little better. Where was I? Oh, here. Oh, this gives us a value of 0.003714. Then you go to the Moody diagram, you go up to a little under 0.004, and go straight across. Gives a friction factor of about roughly 0.027. I think that's everything I need. Yeah. Okay, cool. All right. So now it's just algebra. So I'll just plug this in my calculator real fast and it should spit out a V value. is equal to 13.37 meters per second. Then also Q is equal to AV, so 0.00385 meters squared times 13.37 meters per second. Therefore, part A, nope. Q is equal to 0.0515 meters cubed per second. Oh, fuck. Sorry. Cool. All right. Part A done. Now show that the observation for fully turbulent flow is correct. Part B. Just find Reynolds number. If Reynolds number is greater than, forget if it's 2,000 or 4,000. No, it's for something else. It's 4,000, but yeah, pretty sure it's 2,000 for a pipe. What is it again? Rho V D over mu. So now that we have V, we can actually find this. Rho is 999 kilograms per meter cubed. V is 13.37 meters per second. D is 0.07 meters. Then mu, from the front of the book, the viscosity. Yeah, dynamic viscosity is equal to 1.12 10 to the negative third. Newtons per second. Squared. Sorry. Squared. Solving for Reynolds number. $8,000, 834,789. So well over 2,000 more for 1,000. So it's just obviously turbulent. Also, if you look at the Moody diagram, it puts it well over into that section on the right where everything is wholly turbulent. Yeah, so that's part B. Part C. The pump is 70% efficient. Determine how much power must be supplied to the pump. So efficiency is defined as rho G Q head gain from the pump over shaft work power from the shaft. So basically, like, top is what you're getting out, the bottom is what you're putting in. So we can rearrange this. work shaft work equals rho, which is 999. Gravity. Volumetric flow rate. Times the head gain, which is the equation 20 minus 2000 times Q. Squared. All of this over 0.7 or 7%. So the necessary power that must be supplied to the pump equals 10,585 watts, or 10.6 kilowatts. And that's it. Seemed to fit. Something that worked. Sorry if that was miserable to listen to, but trust me, it was way more miserable to do. But now I'm done with the semester. I'm going to go take a nap.